Hello, everyone. So up through trigonometry 006, we've managed to define the 6 trig functions in terms of a right triangle and their various ratios of sides for a given specific angle. We've managed to then make at least, I think I've made one identity there. I mentioned another. I managed to make the graphs of the trig functions. I managed to make the unit circles of the trig so that we can use them to define the trig functions. I even sort of laid out ways you could do the graph of cotangent, secant, and cosecant, even though I didn't actually do that. I just showed it to you on Desmos, but they're very straightforward to do, and I do recommend you take the time to definitely graph them by hand sometime, not just by Desmos, but do it by hand. Actually make X and Y points on a graph, piece of graph paper, and do those. Well, now I want to go back and look back at our original trig function definitions and see what things we can learn from it to learn some very basic identities, and then later we'll try to soup up the identities. So to do that, let's turn on my document cam. The first thing I want to do is draw my right triangle like I've been representing. And the way we've been doing that, if I can get this into focus, let me put a pin down there, see if I can get a little better focus. I hope I turn the light on. Okay, that looks pretty good. So if I take a triangle, I can draw it way out here. And it's going to be a right triangle. This is the 90-degree angle right here, so that makes this the hypotenuse. If I call this the angle theta, then this side, I'm going to call this side, by the way, the adjacent angle. But I'm also going to call it A. I'm going to call this side the opposite side, but I'm also going to call it B. And then I'm going to call this side, notice the arrow, this thing looks like an arrow a little bit, and it points at the hypotenuse. So I'm going to call it the hypotenuse, but I'm also going to call it C. So some things we already know about right triangles is, for instance, the Pythagorean theorem. A squared plus B squared equals C squared. So that's kind of helpful. We've also learned that in some ways people go so, ka, toa. We've learned that as well, which I do some old horse came hopping through our alley, and that's why I introduced the adjacent side, the opposite side, and the hypotenuse, so you'd know that. But what that translates to is sine of theta equals opposite over hypotenuse, which is B over C. Cosine theta is equal to adjacent over hypotenuse, so that's A over C, and tangent theta is equal to opposite over adjacent, which is B over A. So those are our basic trig functions. I also told you that the trig functions cotangent theta was equal to 1 over tangent theta. I told you, and of course that's equal to adjacent over opposite. I told you that secant theta is 1 over cosine theta, and that of course means it's C over A. And I told you that cosecant theta is equal to 1 over sine theta, and of course that's equal to C over B. So we can automatically see a few things. One, I already showed you, I've done it twice now, but basically if you take sine theta and divide it by cosine theta, you end up getting B over C divided by A over C. And remember, when you divide by a fraction, that's the same thing as multiplying by the reciprocal of that fraction. So I'm going to take that bottom one and flip it over. I'm just going to take B over C and write it as is. And I converted that division into multiplication. And you get B over A. Well, if you look over here, you see that B over A is in fact tangent. So we now know that sine theta over cosine theta is equal to tangent theta. We use that to graph tangent just in the last video. Of course, you can also see that if you divide cosine by sine, you're going to get cotangent theta. So there's a couple more identities. So we've now got those. Now here's something neat. If we take A squared plus B squared equals C squared, if we take that and divide it all the way through by, let's divide it by C squared. So I multiply both sides by 1 over c squared. When I do that, I get a over c squared plus b over c squared equals c over c squared. Well, a over c, I think you recognize that as cosine, and b over c is sine. So we end up getting, I'm going to write it in a different order because I'm used to writing it in a different order. I'm going to say sine squared theta plus cosine squared theta, and c over c is just 1. So that's an identity, okay? And notice how you write the exponent on the trig function. You write it on the word, not on the theta, because that could be confused with whether you're taking the square of the thing inside of the sign or if you're taking the square of the whole thing. So that's another identity that's very helpful. This is one of the Pythagorean identities. If I took a squared plus b squared equals c squared and multiply both sides by 1 over a squared, what we would get is a over a squared plus b over a squared equals c over a squared. And I think you can see this is 1. B over a, of course, is tangent theta, and c over a, of course, is secant theta. So what we just discovered is 1 plus tangent squared theta is equal to secant squared theta. So that's another important identity. These 3 that I'm getting ready to do, I've done 2 already, this one and this one. They're called Pythagorean identities. We've also have these identities, which are kind of nice. And now if I do the other thing, I've divided the Pythagorean theorem by c squared, and I've divided it by a squared. So let's go ahead and try dividing it by b squared. So if I take that Pythagorean theorem again and say a squared plus b squared equals c squared, and divide both sides by b squared, I'm going to get a over b quantity squared plus b over b quantity squared equals, and in this case it's c over b quantity squared. This a over b, you'll notice, is in fact cotangent squared. This b over b is 1, and this c over b is cosecant squared. So we've got another one. I'm going to write it the same way I did before. 1 plus cotangent squared theta, a over b was the cotangent, is equal to cosecant squared theta. So we've now gotten 5 different identities just from these basic equations. Well, another thing we can see is that since sine and cosecant are reciprocals, if we multiply the 2, sine and cosecant are reciprocals. If we multiply the 2, we should get 1. So these 3 are called the Pythagorean identities because they came from the Pythagorean theorem. Now I'm going to do another one. So let's do sine theta times its reciprocal, which is cosecant theta, is equal to 1. There's another identity. Also, cosine theta times its reciprocal, which is secant theta, is also equal to 1. Anytime you multiply a number by its reciprocal, you get 1. That's the definition of reciprocal. And then finally, tangent theta times cotangent theta is equal to 1. So we've now gotten a total of 8 identities. And there's a couple more basic ones that I really want to get, and they are from the triangle itself. If you remember a triangle, the angles in a triangle have to add to give you 180. So here's theta, here's 90. So this 90 is already counted for 90. So these other 2 must have to account for 90. So this angle up here must be 90 minus theta, or pi over 2 minus theta. So I could say this angle up here is pi over 2 minus theta, whereas this angle was just plain theta. Well, we see that the sine of theta is opposite over hypotenuse, but the cosine of this function, of this angle right here, is adjacent over hypotenuse, which is the same, excuse me, adjacent over hypotenuse, which is the same thing as the sine. So we see that the sine of theta is equal to, now I'll put this paper down here. The sine of theta is equal to B over C, but that's also equal to the cosine of pi over 2 minus theta, because the adjacent angle for the co-angle is in fact the opposite side. So we now have another identity, and that is cosine pi over 2 minus theta is equal to sine of theta. We can also do that again with another trig function. In this case, we can take the cosine of theta. That's equal to the adjacent over the hypotenuse. So that's the A over C. But lo and behold, that's also equal to the sine of the coangle, which is pi over 2 minus theta. So from that, we get the sine of pi over 2 minus theta is equal to cosine theta. That's another identity that's helpful. And if we take the tangent of theta, that's equal to opposite over adjacent, which is B over A. But B over A is also equal to the cotangent of, which is, remember, opposite, adjacent over opposite. That's the cosine or the cotangent of the coangle. So that's pi over 2 minus theta. Sorry about that. That means that cotangent of pi over 2 minus theta is in fact equal to tangent theta. Now we can do the cotangent of theta, which is adjacent over opposite, so that's A over B. Well, that happens to be the same thing as the tangent of the coangle. So the tangent of the coangle is opposite over adjacent, so that'd be A over B as well. So we see that's absolutely right. See, tangent opposite over adjacent would be A over B. So that's also correct. So we finally have tangent pi over 2 minus theta is equal to cotangent theta. And that's about all we can get just from looking at these individual trig functions in the triangle itself. We can start to manipulate them. We can use these various identities to find out other things. We can also use neat little tricks to represent sines and cosines as exponentials. And when we do all that, then we can start to find even more identities. But this is a really good start for identities, and you can do a lot of things with it. We've got tangent theta equals sine over cosine, cotangent theta equals cosine over sine, sine squared plus cosine squared equals 1, 1 plus tangent squared equals secant squared, 1 plus cotangent squared equals cosecant squared, sine times cosecant equals 1, cosine times secant equals 1, tangent times cotangent equals 1, and then we've got these four beauties. So I think that's a really good start for getting you used to using trig identities and even knowing where they come from. If you go through this process that I did, these identities, if you do it a couple times, these identities will be stuck in your head for a long time. So I hope this helps you all in trying to wade through your pre-calculus course or your trigonometry class, if such classes still exist. It's almost always just plain pre-calculus, but trigonometry is a cool course all by itself. We can do neat things like vectors, and which we use to add forces together, or we can use to do survey work, so you can figure out how far the distance is across a lake that you don't actually want to cross, all sorts of cool stuff. So I think trig's sort of the one math where you immediately start seeing applications and you can immediately enjoy it. So next time I'll do laws of sines and cosines, I think, and that's it. Have a good day.